Olá a todos and welcome to another video of Julia Journey Juggling Joyfully. In today's video we're going to talk about multiple dispatch, at least an introduction to it because we're only going to spend 10 minutes on this. It should be enough to give you an idea of why these things are so important to Julia. We're going to start by implementing a simple function to compute the quadratic roots of a quadratic equation. So you have an equation which is something like ax squared. I can use some Julia notation here, bx plus c equals 0. And by the way, what I just did is backslash circumflex 2, and then you press tab and this appears. Okay, I'm gonna just leave this here so you know in the future. Quadratic roots, essentially computing the solution to this, and the solution is given by computing delta. Same thing, you can just backslash uppercase D, delta, tab, and you have the delta symbol, b squared minus 4ac, and the solutions are minus b plus minus the square root of delta over 2a. By the way, if I have not mentioned this before, in Julia you can write these Unicode characters easily with these tricks, depending on the editor, of course. As I mentioned in the first class, some editors have support for Julia, and one of the things they support is writing Unicode characters by giving backslash and a specific name like delta. But also in Julia, you can use these Unicode characters as variable names. So I can say delta is equals to b squared minus 4a times c. You cannot do this squared to signify the squared. That's not allowed. But you can do 4a, and that's understood. The error up here is because of this symbol. It tries to run this because it has a single backslash. So this probably should be a comment somewhere instead of a actual string. And now we're going to do the following. If delta is greater than 0, then we're going to return minus b plus the square root of delta divided by 2a, and minus b minus the square root of delta divided by 2a. But what happens if delta is negative? You have two approaches here. The first one is to use the earlier math, which is to say that there is no solution. And the second one is to use later math, which is to say you can use complex numbers, and you have the square root of -1 to be the imaginary number and continue from there. So here we're going to do the second one for reasons, and you can do that easily here by computing the square root of the complex delta. So when you do complex delta here, so like this, if you say complex of 1, you create a complex version of the number 1, which is 1 plus 0 times the imaginary number. The good thing about this complex is that you can compute the square root of it, and it understands. So the square root of -1 in the complex is 1 imaginary. If you try to compute the square root of -1 without that, you have a domain error. The square root is not defined for real negative numbers. Okay, let's remove this. So in this case, I'm gonna do this, and then this, and then this. Okay, so I could probably also do this. Let's test this function. So quadratic roots of 1, -5 and 6. This is my traditional example, 3 and 2. So these work for different roots, 1, 4, and 4 for roots which are the same, and 1, 0, 1 for imaginary roots or complex roots. Have 1 imaginary and -1 imaginary. So this works as well. So this function has an issue though. In Julia, you have something called type inference. So we did not have to specify the types of this function, But when Julia does the compiling internally, it uses something called type inference to determine the types of the output for this function. So it compiles it and it says, hey, this function is a function that receives, in this case, 3 integers, and it returns something, okay, of a given type. And you can use something called a macro code warn type, or just code type, but in this case we want the code warn type, to see the types of these numbers. So to see the types of these values. So here we have the quadratic roots of 1, minus 5, and 6. You have a lot of things going on here, but this is what we want to focus on. The arguments a, b, and c are of type integer 64. You have some locals, the value of r, which is a union of float 64 and complex f64. The value of delta, which is always an integer for this input. So I want to determine the type of the output from the type of the input, and that's the issue here. We cannot decide whether we're going to have a complex number or a real number as output. And because of that, Julia is using a union of these two types. So this is a warning. So this is like yellow, which is like, this is not so great. Newer versions of Julia, so if you do the same thing in earlier versions, you're going to have a worse inference. Depending on the version. Essentially, Julia improves this type inference with every new version. So this is bad, but not terrible. You should be aware that this can be a very bad issue for your speed. If you have issues with type inference, it can harm your code a lot in terms of performance. And by the way, you can follow through all of the construction of these values to know where things became a specific type or another. In some cases, you might want to do that. There's also a package called Cthulhu, yes, like the creature, Cthulhu JL. If you want to debug your code, you can use Cthulhu JL. It is very complicated to do that, so that's not something you want to do in your first weeks of using Julia. But if you already know your way around Julia, this is a reminder that this package exists, and you can have your slow descent into madness. So let's say that we are in an earlier version of Julia, or in more realistic case, that you have something that is not simple. How do you solve this? You want to solve this by making sure that types of the input are taken in consideration when you do things. Here there's a glaring complex being called. So this is obviously converting things to complex. So it's kind of obvious that this, or essentially this branch, is the issue. And the problem is that we, in some cases, return real values, and in some cases we return complex numbers. The solution is to not do that. We either only return real values or only complex number. Now we get to multiple dispatch, which is how can I have both those things at the same time and still solve this issue? So here what I'm going to do is I'm going to have two versions of the same function. So in other language, I could have, for instance, quadratic roots real and quadratic roots complex, right? So for the real part, if delta is positive, that's fine. Otherwise, I'm gonna raise an error. Let's do a simple raise error here, which is just called the function error, not real. And for the complex case, we actually don't have to do anything. We just do this, and we assume that it works. There is still the issue here that maybe delta is not complex, so you could force it to be complex. So now it's always going to be complex, no matter the input. And this assures that the output is going to be complex as well. So this is one way of solving it. Another way of solving it, which is more interesting and more Julia-like, I guess, or more Julian, is to give specific types to the input. So in Julia, you don't have to give types, but you can if you want to constrain the arguments. So here I'm gonna say that this has to be a real number. So quadratic roots has 3 arguments. All of them are real numbers. This can mean float, integer, doesn't matter, and they don't have to be the same type. So when this happens, I'm essentially calling the real version of the function. And for the other one, I can simply not give types, and I can actually just ignore this part as well. And when I don't give types, I'm essentially saying, hey, if this is not sufficient, so if the types are not all three real, then use this function instead. If I save this and run, you can see that this worked. If I change this to complex 1, for instance, this is calling the other function, this one here, and you can see that the output is 3 plus 0 im, which is a complex number in the sense of Julia types, although the numbers are real in the mathematical sense. And by the way, here you have quadratic roots of 1, 0, 1 not working anymore because it has a non-real solution, but you have at least one of those terms as a complex number. You can see that now it works, okay? Interesting, you also have the code warn type for this. No, so quadratic roots 1, minus 5, and 6 always is going to return a tuple of float 64. If I have a 1.0 here, the output is a float 64. If I have a complex 1 here, it's actually a complex float 64 now. Okay, so it can always know the type of the output given the types of the input. This is what's called a type stable function. So let's stop here for now. Types are very important in Julia, and multiple dispatch is one of the main features of Julia. So of course we're going to talk a lot more about that when we go into future videos. I also have another video, which is much longer than this one, talking about how I use Julia, modular arithmetic, and linear algebra to solve an RPG puzzle. And that's essentially an in-depth video about types. We define a new type there, we define ways that that type interact with existing things, and we use multiple dispatch to allow Julia to do essentially linear algebra things with that type. Well, thanks for watching today's video. I hope you enjoyed it. Please leave a comment if you want to know more, if you have more questions. Please like and subscribe, and remember to press the bell button to be notified of future videos. I'll see you next time. Bye bye.